Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at constructible numbers. So we call a number k constructible if we can make a line segment with that length, exactly that length, using a straight edge and compass. So think of a straight edge just as a ruler. So it turns out all rational numbers are constructible, but not all constructible numbers are rational. So we'll go through what that means in a second. So an example would be using a straight edge, you can make a line segment of, say, length 4. So that means 4 is a constructible number. So using a straight edge, you can also divide this. So for example, we could divide this into fifths. So of course my diagram here isn't exactly accurate. I can't use a ruler on my iPad, but you will be able to. So if the whole segment was of length 4, we've divided into fifths. Each of these will be 4/5. So this will be 4 fifths. The next one will be 8 fifths, which is 1.6. And then we're adding 0.8 or 4 fifths each time. So we can use a straight edge to calculate other lengths. If we can do 4, if we can do a line segment of 4, we can do, for example, line segments of length 4 fifths. Because a straight edge will allow us to divide. So a straight edge, of course, will allow us to add and multiply. So if we can do a line segment of 4 fifths, we can just combine 2 of those segments to make a line segment of a sixth, or we can combine 3 of them to make a line segment of length 2.4. So basically, using a straight edge and also a compass, what it allows us to do is it allows us to add, multiply, subtract, and divide line segments of a given length. Now, it turns out if you add, subtract, multiply, or divide, except by 0, rational numbers, you get another rational answer. And that's why all rational numbers are constructible. You can construct a line that has length any rational number. You can construct a line whose length is a half, or is 3/2, or is 2.3 recurring. So for example, 2.3 recurring, as we might know, is 8/3. We can use a straight edge to construct a length of 8, and we can divide it into thirds. That's why I can construct a line that has length exactly 2.3 recurring, whatever units, centimeters, millimeters, whatever. So all rational numbers are constructible. But it turns out not all constructible numbers are rational. It is actually possible to construct line segments with length k where k is an irrational number. So let's look at doing that. So we're now going to show that the square root of 2 is a constructible number. Even though root 2 is clearly irrational, we can easily create a line segment whose length is exactly square root of 2. So the first one I'm going to show you involves Pythagoras. See, 2 is just 1 squared plus 1 squared. So by Pythagoras, if we construct 2 line segments at right angles, each of whom has a length of 1, Pythagoras' theorem says if we join up this third side, it will be the square root of 1 squared plus 1 squared, which is root 2. Of course, you will be able to do this a lot more accurately than I can do, but this can be done just using a straight edge. It turns out there's another way to do it using similar triangles. So we can start by drawing a circle. We can choose the diameter using a compass and a straight edge. Use the straight edge, use the ruler so that you can make sure the compass is far enough apart, and then you can draw a circle with a given diameter. So if we draw the diameter here, what happens is if you go 1 unit, 1 centimeter, whatever, from the edge of the circumference, and you draw what's called a chord here, you draw a line from the diameter to the circumference, it turns out by similar triangles, which I'll draw here, that if this length here is k, so k goes from there to there, then this length here must be root k. That's just by similar triangles. So if you wanted to construct a line segment with length root 2, you would just make this length 2, and this would be root 2. You would just draw a circle with diameter 2 plus 1 is 3, and then 1 unit in from the circumference on the diameter. If you just draw a chord up to the circumference of the circle, it will be root 2. So just replace k here with 2, and you have a green line segment here whose length is the square root of 2. Of course, this would extend to the square root of any rational number. Because we can draw a line segment whose length is, say, 2.3 recurring, then we can perform this task and we can construct a line segment whose length is the square root of 2.3 recurring. So because we can add, subtract, multiply, and divide the lengths of line segments using straight edges and also compasses, if we can create a line segment of length root 2 and we can create a line segment of length root 3, we can easily create a line segment whose length is root 2 plus root 3. So if we wanted to use Pythagoras, we would just adjoin this here. So note 3 is not really the sum of two squares, but it is the difference of two squares. 3 is 4 minus 1. So we'll adjoin to the square root of 3 another right-angled triangle. It's going to have hypotenuse 2 and shorter side 1, because 2 squared minus 1 squared is equal to 3. So by Pythagoras, square root of 2 squared minus 1 squared will give us root 3. So for this one, you have to make sure this is one continuous line. Again, I wasn't able to do that with a straight edge and compass. This one's a bit harder to do because we have to get the angles right there. So to make a line segment of length root 2 plus root 3, it's probably easiest to use this method. So we could just do it once with this being 2, and then we could draw another circle around here and create one up here that's root 3. So of course, because we can create a line segment whose length is root 2 plus root 3, we can also create another line segment whose length is the square root of root 2 plus root 3. We can just use this as like the diameter of our circle, the value of k, extend it by 1. We create a circle with that diameter. So if k was root 2 plus root 3, this would be the square root of root 2 plus 3. So hopefully you're getting an idea now for why constructible numbers include all the rationals, but also really anything involving square roots. Now, note that constructible numbers don't include things like cube roots. We can't use things like Pythagoras to construct, say, the cube root of 2. We also can't use this method to create one that's the cube root of 2. So cube roots of non-perfect cubes, like cube root of 2, cube root of 7, they are not constructible numbers. The only real constructible numbers involve rational numbers and square roots. Another example of a number that's not constructible is pi. Now, it's actually very simple to make a circle with circumference pi, because remember that the circumference of a circle is diameter times pi. So if I were to create a circle and its diameter was 1, that's pretty easy to do, the circumference here would be pi. But when we're talking constructible numbers, we're talking about line segments. So though it's easy for me to create a circle whose circumference is pi, it's not possible to construct a line segment whose length is exactly pi. Now, when I say I can't construct it, I mean it can't be constructed using a straight edge, a ruler, and a compass. Of course, nowadays, Computers will probably be able to do this without using a compass and a straight edge, but when we're talking constructible numbers, we're only talking about numbers for which we can create a line segment with that length using a straight edge and a ruler. So pi is not a constructible number, even though you could easily draw a circle whose circumference is pi. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.